In this video, we're going to look at AP Practice Problem F, which is primarily a table question. To be careful, they do give you a function, but given the units on this, the function looks like it's already a derivative. It's cubic feet per minute. And I haven't even read what it is, but if I do read what it is, it's grain being added to a silo. So there's some silo, they're pumping grain into it, and the rate at which they added is modeled by this g of t function and cubic feet per minute. So g of t is the rate at which grain is going into the function. So essentially g of t is a derivative. They just didn't call it g prime. The original function was grain. They didn't give us a name for that. They just basically said there's original grain function and its rate of change is now called g of t. And once again, they don't even give us an analytic version of it, meaning we don't have an equation. We're just stuck having selected values of it. So we know at certain given times what the rate of grain going in a cubic feet per minute is. So here, like at time 0, they're pumping in 12.8 cubic feet per minute, and then it's going up and down as time goes on. And this is for the first 8 seconds, first 8 minutes, that they make sure to tell you that it's valid between those times. So outside of this interval, we don't really know what's going on. So part A is to actually approximate the value of g prime of 7. Now the thing you have to be careful with is g is already a rate of change. It's cubic feet per minute. We want the rate of change of the rate of change. That's what the derivative gets us. The derivative gets us a rate of change, but we're getting a rate of change of what's already a rate of change. So that makes the units a little screwy, which we'll talk about. But basically they want how quickly these rates are changing. That's g prime of 7. In order to approximate it, 7 is on this interval between 8 and 6. So my best approximation is to do the average rate of change, or the slope, between these 2 points. So g prime of 7 is approximately g prime of 8 minus g prime of 6 over 8 minus 6. That comes out as this quotient, which gives you 2.2. So you get a point for getting that numerical value 2.2. Once again, if it's the AP exam, you don't have to actually simplify numbers. Once the number's in, you can leave it. So this is technically an answer as well. They'd have to give you credit for. Then comes the interpretation. So this is the part that's a little screwy. What is happening? What does g prime of 7 mean? It means at time 7, the rate of change of grain is actually changing. It's increasing. So not only does it have a rate of change, but that rate of change is going up, which you can kind of see because by 1 it is. Now it doesn't necessarily, because they want it's 7. Between 6 and 8, it does go up 18 to 22. Now that's not proof at that spot that it's happening, but this, according to what we know, as best we can tell, the 7 is basically part of this slope that's going up, and this is the slope of the rate of change of this. So the rate of change is actually increasing. So now, since the rate of change was already cubic feet per minute, and it's changing per minute, the units are literally cubic feet per minute, because basically this cubic feet per minute is changing every minute to be greater, according to this, by 2.2. So instead of saying per minute, we just put double down on the minutes down there, basically multiply them and square it. So since it was cubic feet per minute, if you take another derivative with respect to time, you're sort of putting another factor of minutes down there. And so the proper units are cubic feet per minute squared. Okay, so a little weird, but they're basically trying to trick you here, making you think, well, oh, the derivative is the rate of change, it's cubic feet per minute. But once again, it's the rate of change of the rate of change, cubic feet per minute squared. Let's move on to part B. Part B, they say write an integral expression that represents the amount of grain added to the silo from the times 0 to 8, and then we want to approximate that using a right-Riemann sum with the intervals indicated by the table. Basically, the table gives us certain sample values, so we're not going to be able to get the exact integral, but we should be able to approximate it. Now, first part's to set up the integral. Well, what's the amount of grain? It is the integral of g of t. G of t is a rate of change. If you integrate a rate of change, you go back to the original function. So this is grain per minute. If you go backwards, you just get grain in general. What's the grain quantity? So notice that taking the derivative made it grain, cubic feet per minute. This is cubic feet per minute. Going backwards just makes it cubic feet. So this integral gets you a point. Just writing that you need to integrate from 0 to 8 of g of t dt to know the value gets you that. Now, you can't know what this exact value is because they didn't give you any kind of exact function. They did give you this table, and basically you want to find the area under the curve using Wright-Riemann sums, basically right rectangles. So I modeled it with a picture, though AP-wise you should show I believe they want to see the calculation, like how did you get those areas and how did you get the overall area. But the picture, I think, at least illustrates graphically what's going on. I put all the y values at the selected spots. In a Wright-Riemann sum, you want to make the height of the rectangles the right side. So I'm ignoring the 12.8. This rectangle is going to be 15.1 high and 1 wide. This one's 4 wide using the 20.5, 1 wide using the 18.3, and the last interval will use the right side there, which is 1 by 22.7. So basically I get these 4 rectangles. The 12.8 is the only one not used, but all the other ones are. These 4 rectangles have these 4 areas, which if you calculate and add them up, get you the last point, which is 160.8 cubic feet. Once again, you don't actually have to simplify numbers on the AP exam, so technically putting this is both the area work, and the answer, but that is the simplified answer, 160.8 cubic feet. So that gets you 3 points. Then they give us a new function, and they finally give us an analytic function. Basically, what I mean by that is instead of giving us samples in a table, they give us an actual continuous function we can work with. So the grain in the silo spoiling at this rate. So now we have basically the grain in the silo becoming unusable, transforming or rotting or whatever. Kind of gross. They always come up with great examples in these problems. So it's modeled by this weird trig function. Now this is a calculator active question, as all questions will be on the 2020 exam, because they can't stop you from using the calculator, so they just allowed it. The important thing is make sure your calculator is in radian mode, because basically all things in calculus, the default measurement's radians. We don't want to do this in degrees. So you're going to use a calculator for this because it's a lot easier to do this in a calculator than it would be to try to calculate its antiderivative. If you could even do that, it looks pretty difficult. So this is our spoiling function. It's valid for that same time period that we're talking about, the first 8 minutes. And we want to approximate the amount of unspoiled grain that's in the silo. So you got to read that carefully. So what's the amount of spoiled grain? It's basically similar to this question. They gave me the rate. Once again, this is the rate at which the grain is spoiling. If you integrate the rate, you get the original value. So when I integrate this rate of spoilage for that amount of time, it tells me how much spoilage happened. It's approximately 99.051 cubic feet. So this is how much is spoiled by time 8. So how much is not spoiled? Well, I already know, I have an approximation, I guess. And once again, they do want the approximate amount because you can't find the exact amount. So there's approximately 160.8 cubic feet of grain that was pumped in, but now this tells me 99.051 of it spoiled. So if I subtract those, the leftover is 61.749 cubic feet, and that's the amount that's unspoiled. Hit the last question. They say, based on the model in part C, is the amount of unspoiled grain in the silo increasing or decreasing at time equals 2? Show the amount of work that leads to your answer. Now, the thing you have to consider is, you might think, oh, well, there's grain in there and it's spoiling, so if the spoiling amount's going up, the unspoiled amount should be going down. But remember, they're pumping more grain into here. Even though it's spoiling, they could be adding more fresh grain than what's spoiling. So basically what you need to consider is you have to consider how much fresh grain is being added at what, or basically what rate is fresh grain being put in, and then at what rate is it spoiling. If the rate of spoilage is higher than the increase of fresh grain, then you're gaining spoiled grain. If the increase in regular grain, the amount of grain that's going in, is greater than the spoilage, well, then you're actually adding fresh grain to it. So I basically have to look at both of those rates, which they gave me, at time 6. The rate of increase of the grain is up in the table. And you don't have to take any derivative for this because they already gave you the rates. Like I said, G of t and W of t are already the rate, so I just need to evaluate them. How much is G of t, the rate of increase of grain? Well, it's 18.3. That's up here in the table, so you can just read that right off. What is the rate of spoilage? Well, using the function from part C, plug in the 6, and here's the rate of spoilage. So now here's what you need to consider. There's fresh grain going in at a rate of 18.3 cubic feet per minute. It's spoiling a rate of 16.063 cubic feet per minute. This is the bigger value. So basically, if you want to be official here, you want to consider what's the rate of unspoiled grain. It's basically the fresh grain minus the spoiled grain leaves the unspoiled grain. So if we subtract those rates, this leaves a rate for unspoiled grain. The unspoiled grain is actually increasing by 2.237 cubic feet per minute. So basically, the rot is not happening fast enough to counter the addition of grain. So really all you need to know about this rate is you don't even need its exact value. You just need to know it's positive. So since it's positive, it means the unspoiled grain rate's going up. Had it been negative, it would have been going down. So since the rate of change of unspoiled grain is positive, I answer their question. The amount of unspoiled grain is increasing. It's basically, what they wanted to know, was it increasing or decreasing? So due to a positive rate of change, it is increasing. So even though they're gaining unspoiled grain, they're also gaining spoiled grain. They're also gaining unspoiled grain in the silo because they're adding it in pretty fast. Okay. I don't know if I talked about the point totals in a while. I think this one was the last time I talked about point totals. So the integral here gets you a point, and then this, I don't know why I have it marked here, this value gets you the second point. And then on this problem, basically considering some kind of difference of the rates gets you the point. It's basically the concept of needing to know, this is bigger than this or vice versa. And then making your conclusion is the second point on this. So that gets you a total of 9 points. All right, pretty standard table question where they really basically started with a derivative and got to, even though it's not marked with the prime, this is a rate of change function. They were able to go back and forth asking you the rate of change of the rate of change, integrate gets you the amount, did it again, and actually got you to compare rates to see what's going on. All right, so I said a pretty comprehensive question. Something they like to ask, like as I said, they love tables as much as they love pictures and analytic functions. All right, so hopefully that explains out the problem and lets you know what you need to know to solve a problem similar to it. All right, be on the lookout for AP Practice Problem G in the next video.